All right, I wanted to scroll ahead in the chapter a little bit and look at the energy for an electron that's in level n. So for this equation, K is a constant, Z is the positive charge that's in the nucleus, and N is the level that the electron is in. All right, I wanted to take a look in your textbook at figure 6.14. This is the representation of the energy that an electron has in these various levels. So this N is the number that comes after the comma. So we have level 1, level 2, level 3, and so on. So these numbers are getting more and more negative as you go down. The lowest energy state is to be in level 1. So if we normalized the exponents so that they were all 10 to the negative 19, this would become negative 21.8 times 10 to the negative 19. This would become negative 0.872. The magnitude is increasing. They're becoming more negative as you go down from level 5 to level 1. So the lowest energy state is to have the electron at level 1. Also, the spaces in between the levels decrease as they go up. So the space between 1 and 2 is much larger than the space between 2 and 3, which is in turn larger than the space between 3 and 4, and so on. So what we're going to focus on is the change in energy. So an electron can go up in energy. Remember, the lower levels have the lower energy. So if it absorbs some light or some electromagnetic radiation, if it absorbs some energy, it can make some jumps up from 1 to 2, or from 2 to 3, or even from 1 to 3, or further, other levels. If some energy is emitted, then that means the electron is dropping down in energy level. So the change in energy level would be the energy where it ends up minus the energy where it started. Just like delta T in chapter 5 was the final temperature minus the initial temperature, the change in energy is the final energy minus the initial energy. And if delta E is negative, that would be like these purple arrows where the energy is going down. If delta E is positive, that's some of these green arrows where the energy is going up. So the E final, that would be negative k z squared over n, and we put an F here for the final level. And then we subtract the initial energy level, and the initial energy level is negative kz squared over ni squared. So these two negatives become a positive, so that it ends up being negative kz squared over n final squared plus kz squared over n initial squared. So we can reverse the order maybe. Since the term with the n final is negative, we can just write this as kz squared n initial squared minus kz squared over n final squared. And then we can take the kz out like this. Since the kz squared is in both terms, we can take it out and have this be kz squared 1 over n initial squared minus 1 over n final squared. For hydrogen, the proton charge in the nucleus is just 1. So 1 squared would just be 1. So if we replace this z squared with 1, we would just get k. And this equation appears a little bit earlier in the chapter. At the beginning of section 6.2, we have this where the change in energy, here we have the change in energy, that's what we started out figuring out, is k times 1 over n initial squared minus 1 over n final squared. So it's going from level n1, n1 is the n initial, to n2, that's where it ends up, that's the n final. So this matches this equation. And this equation, if it's not hydrogen, we would have to keep the z squared in there. A couple of the end of text problems have examples where it's not hydrogen. I'm going to stick to hydrogen, but if you're doing some of the problems in the back of the chapter, then be careful for Z. You have to use Z in this equation if you don't have hydrogen, if you have a positive charge in the nucleus other than 1. Let's relate this back to another formula that we saw not too long ago. This change in energy is being emitted or absorbed as a photon of light, of electromagnetic radiation. And for light, the energy is Planck's constant times the frequency. And since we've mentioned before that the frequency is the speed of light over the wavelength, the energy is Planck's constant times the speed of light over the wavelength. So this change in energy, which is k times 1 over n initial squared minus 1 over n final squared, if we replace that energy with Planck's constant times the speed of light over the wavelength, we can divide both sides of the equation by hc. On the left side, that gives us 1 over lambda because the hc's cancel. And this equation over here for 1 over the lambda, the wavelength of the light that's either absorbed or emitted, is an equation. This is very similar to an equation we saw at the end of section 6.1. So we saw this equation with the Rydberg constant. So that is very similar to this equation if k over hc is equal to the Rydberg constant, which for hydrogen it is. So I just wanted to take a look at how all these different equations and formulas are related here. Mostly the energy one is the most versatile, I think, for either absorbing or emitting different light. And so then once you have the energy, you can figure out the wavelength, or you can figure out the frequency of the light that's being emitted or absorbed. So now that we've talked a little bit about how these formulas are related, let's go ahead and use this particular formula, the energy one, to figure out the energy change of an electron going from one level to another. So remember that N1 is the initial level. It's going from level N1 to level N2. So this is the initial level where it's starting. This is the final level where it's ending up. So if an electron is going from level 2 to level 1, these are the terms that would be inside the parentheses. And remember K, we have this constant of 2.179 times 10 to the negative 18 joules. And then this would be 1/4 minus 1, which would be a negative 3/4 or negative 0.75. And so that would make the energy change. So this change in energy is equal to negative 1.634 times 10 to the minus 18 joules. And since it's negative, this energy is being emitted. And we have calculated the energy change of negative 1.634 times 10 to the negative 18 joules. And now we want to know the wavelength of a photon that has this energy level. Alright, so we have the energy. How is it related to the wavelength? How do we come up with the wavelength from the energy? So we've used this equation before to come up with the energy from the frequency and also from the wavelength. Because remember, the frequency and wavelength are related because the product of the frequency and wavelength is the speed of light. So the frequency is the speed of light over the wavelength. We can replace that frequency in this equation with the speed of light over the wavelength. So we have E equals hc over lambda. To get the wavelength lambda alone, we can first multiply both sides by lambda and get E lambda is hc, and then lambda is hc over E. So let's plug this energy in there and find the wavelength. When we do that, we're just going to plug the magnitude of the energy and not the negative sign, because we can't have a negative wavelength. We just have the wavelength of something that's being emitted. And this comes out to be 1.216 times 10 to the negative 7 meters, which would also be 121.6 nanometers if you want to express it in nanometers. Okay, let's go ahead and calculate this energy change for the next problem. So here is our equation. Z squared is actually in this equation, but for hydrogen, Z is 1, so Z squared is 1. So we normally just use the K. And then we have 1 over the initial level squared minus 1 over the final level squared. So we have it going from level 2, that's the initial, to level 3, and that's the final. And K is 2.179 times 10 to the negative 18 joules. And then we have that multiplied by 1 over 2 squared minus 1 over 3 squared. So this is 2.179 times 10 to the negative 18 joules times 0.1389. And that is a positive number. It ends up being positive 3.026 times 10 to the negative 19 joules. Since the energy change is positive, that means it's absorbing energy. The energy level of the electron has to increase. And this photon that's being absorbed, we want to know the wavelength. So we could use the energy and solve for the frequency and then go to the wavelength. We used this equation before to solve for energy directly from the wavelength without going through the frequency. If we multiply both sides by the wavelength, we get the energy times the wavelength is Planck's constant times c, or that the wavelength is Planck's constant times the speed of light over the energy. So let's go ahead and use this equation here. Planck's constant is 6.626 times 10 to the negative 34 joule seconds. The speed of light is 2.998 times 10 to the 8 meters per second. And our energy of this photon is 3.026 times 10 to the negative 19 joules. So the joules will cancel, the seconds will cancel, and we'll be left with meters, which is appropriate for wavelength. And this comes out to be 6.564 times 10 to the negative 7 meters, or 656.4 nanometers. All right, for this next problem, we know the energy, and we also know the initial level. What we're looking for is the final level. So we're looking for NF. This is NI. Level 3 is NI. That's the initial. So let's go ahead and plug these numbers in. The change in energy, it's absorbing, so that's a positive change in energy, 1.816 times 10 to the negative 19 joules. K is 2.179 times 10 to the negative 18 joules. 3 is the initial level, and the final level is what we don't know. So we divide both sides by 2.179 times 10 to the negative 18 joules. That leaves just 1 over 9 minus 1 over n final squared on the right, and this is on the left. When we divide these, the joules cancel, so we're just left with this number, 0.08334. 1 divided by 9, turning that into a decimal, it's 0.1111, and then we still have this unknown term here. If we subtract 0.1111 from both sides, on the left we get negative 0.0277. This is actually a repeating one, so let's do 5 decimal places here so we could go 5 past the decimal here. All right, so let's go ahead and cancel the negative on both sides. We can just multiply both sides by negative 1 to make it positive. And now we can take the inverse. So we'll flip both sides. We get 1 over 0.02777 equals NF squared. 1 over 0.02777 actually equals 36. And so we take the square root of both sides, and we have the final level being equal to level 6. So this amount of energy causes a jump from level 3 all the way up to level 6. So here is a diagram in your textbook, figure 6.15, showing the different energy levels of an electron. When you have a change in energy that's positive, these up-facing arrows, that is showing light or electromagnetic radiation being absorbed. So absorbing energy, giving the electron more energy, puts it in a higher level. When the change in energy is negative, that is when photons of light are being emitted and the electron is dropping down to a lower energy level. Remember that formula we talked about in section 1 always had to have N1 smaller than N2 so that the wavelength could always end up being positive. And the same thing is true here. The wavelength and the frequency of the photon being absorbed are positive numbers, but if the change in energy is positive, those photons are being absorbed. If the change in energy is negative, those photons are being emitted. One other thing to notice here is that the distance between level 1 and level 2 is quite large. So photons that are going from or to level 1 have a lot of energy. These are a large amount of energy. So these long arrows, these larger amounts of energy, are in the UV range because UV radiation has more energy than visible light. So these large changes in energy going down to level 1 or going up from level 1 are in the UV range because that is higher energy than visible light. This was the Lyman series. These smaller arrows going to and from level 2 are the visible light. I'm drawing in some lines that go to and from level 3. These levels, as you go up, the levels are closer and closer together. So the lines going to and from level 3 are even shorter, and so those have lower energy than visible light. Those are in the infrared range. So these arrows highlighted in blue are the smallest energy changes. Those are in the infrared region. The photons being emitted or absorbed have less energy than visible light. They're in the infrared, and that is called the Paschen series. So this equation that describes the energy changes in Bohr's model only works for systems that have one electron. However, you can have a different number of protons. Most of the time we are talking about hydrogen for Bohr's model, but you can have it on helium with a positive charge, so that would be something with 2 protons and 1 electron. Lithium with a +2 charge would be something with 3 protons and 1 electron. These energies are slightly different in that the Z squared cannot just be ignored because it's not just 1. So let's do just a couple of calculations like this. For lithium, Z would be 3. There's 3 protons in the nucleus, so the nuclear charge for lithium would be a +3. K is still 2.179 times 10 to the negative 18 joules. N is the level that the electron is in. So for this one, it's in level 2, and that could be squared. And that comes out to be negative 4.903 times 10 to the negative 18 joules. Bohr also came up with a formula for the radius of the different levels, about how far the electron is traveling from the nucleus. So again, we are going to look at level 2 of the lithium ion. So N is 2. Lithium has a +3 charge in the nucleus, so Z is a +3. So for this radius, it would be 2 squared over 3 times this alpha value, which is 5.292 times 10 to the minus 11 meters. So that would be 7.056 times 10 to the negative 11 meters. So this is a pretty small size for an atom. It's even less than an angstrom, like we talked about before, and less than the wavelength of our visible light that we're working with.